We start this lecture by a quick review of the previous lecture. We said that statics is all about Newton's first law of motion. The first law tells us if the sum of all the forces applied on an object is equal to 0, then the object is at rest or in uniform motion. Therefore, all we need to do in statics is to add up some force vectors. So let's do a quick review on how we were adding up force vectors before statics. Let's say we have vector A. A could represent any vector quantity like displacement, velocity, acceleration, force, and so on. Basically, it could be any physical quantity that is represented by a vector. In general, what is important for us about A are its magnitude and its direction. Both of these properties are encapsulated in the components of vector A along the coordinate axis. So for example, here A is equal to 3i plus j. From this component representation, we can calculate the magnitude of A, which is a square root of 3 squared plus 1 squared. Also, the direction of A is given 3 units in the right direction or toward the east and 1 unit in the up direction or toward the north. So far, having this component representation or alternatively magnitude and direction is all we need to uniquely define a vector quantity. So here's a question. Does it matter where vector A is located in the coordinate system? The answer is no, at least so far. I mean, I can move vector A to the right or left, up or down, or I can move it in any fashion that I like as long as I preserve these two properties, magnitude and direction. This ability to move around vector is very important when we want to do vector calculations such as adding two vectors. For example, let's say we have two vectors A and B and we want to add them up. Vectors A and B are located at two different places. What do? We move them such that they both have their tail sitting at the same point, usually the origin of the coordinate system. And then we use the parallelogram rule to add them up. Or alternatively, we can use the triangle rule. But you can see that using either of those addition rules relies on the ability to move around vectors freely. So here's the bummer. We are not allowed to move around force vectors freely in statics. Specifically, let's say that force vector F is given to us as shown in the coordinate system. Consider a hypothetical line that passes through F. We call this line the line of action for vector F. In statics, we are only allowed to move force vector F along its line of action. We cannot move F in such a way that its line of action would change. So here you can see that the line of action changed, and this is not allowed, at least for now. In other words, before statics, vectors that had the same magnitude and direction were equivalent to each other. So here vectors A, B, and C all have the same components, which ensures us they have the same magnitude and direction. But they have different line of actions that are parallel to each other. So before statics, we would say A, B, and C are equivalent. In other words, A is equal to B equal to C. But in statics, let's say we have three force vectors that have the same components, which again ensure us they have the same magnitude and direction. But they are located in such a way that they have three different lines of action. In statics, F1, F2, and F3 are not equivalent. In other words, F1 is not equal to F2 or F3. Let's clear things up and just consider F1. What we are saying here is that to uniquely define a force vector in statics, we need to define its magnitude, its direction, which both of these properties are uniquely defined by the components, and we also need its line of action. To uniquely define the line of action, we need the coordinate of one point on it. This is because the slope of the line is already given by the direction of the vector. So, all we need to determine the line of action is one point like P anywhere on the line of action. At this point, many questions pop up. For instance, why can't we change the line of action for force vectors? That's a good question. Or, why are we allowed to slide the force vector along its line of action? That's a good question too. Somebody might say that all hell breaks loose here. If we are not allowed to change the line of actions for force vectors, how are we going to add them up using the parallelogram or triangle rule? That's a very good point, because again remember that all of this parallelogram rule was based on being able to move around force vectors without constraint, without worrying about their lines of action. Some of you might say, hey, hold on. You told us we can slide force vectors along their line of action. We just can't change their line of action. So here is how we add up two vectors without changing their lines of action. We slide them along their lines of action until they both have their tail on the same point. Then we use the parallelogram rule. Well, that's true, but I would ask, what if we had to add 3 force vectors? And you might say that we add 2 of the vectors first and then add the third one to the result. So like here, you would add F1 and F2 and obtain the resultant vector. And then you would do the same thing to add the third vector to the resultant vector. But here I would argue again, what if you have many vectors? This process would become very tedious. In addition, I would argue that this approach does not work all the time. I mean, what if you had to add up 2 force vectors that are parallel to each other? They do not intersect each other so that we can use the parallelogram rule. Also, what do we do later when we go to 3D? We will have a lot of vectors that do not intersect each other. Here, I have used this rectangular cube just to represent the 3-dimensional space. You can see that F1 and F2 do not intersect with each other. Okay, I hope that so far you are convinced a little bit that we need a better way to add up force vectors. Also, here's the thing. Even if we always deal with vectors that intersect and therefore could add them up, still this doesn't answer the 2 questions that we asked initially. Why can't we change the line of action for force vectors? And why are we allowed to slide a force vector along its line of action? One note that I want to make here is about adding vectors using the algebraic method. By algebraic method, I mean adding the I components to each other and j components to each other. The problem with this approach is that it just gives us the magnitude and the direction of the resultant vector and does not provide any information regarding where the line of action for the resultant vector would be. So, for example, here a plus b is equal to 5i plus 5j. But this does not tell us where the line of action for a plus b would be. It could be anywhere in the plane. So here's a quick recap. We are not allowed to change the line of action for force vectors for now. Later we will learn how we can do this. You are allowed to slide force vectors along their lines of action. Again, this is for now. In future courses like strength of materials or mechanics of materials, this will not be the case. We have 2 why questions that we need to answer here. And we also said that to define a force vector uniquely, we need to define its magnitude and direction, i.e. its components, and its line of action. And here is another question that we need to deal with. How do we add up force vectors practically? And now, one more thing. The first thing that I have here is actually an interesting video on the engineering of the Golden Gate Bridge. As you might know, the Golden Gate Bridge is one of the iconic engineering structures in the whole world. It really doesn't matter if you are a mechanical engineer or a civil engineer or a student in any other field. I think if you have statics as a course, you will probably enjoy this video. So I leave the link in the description. The second thing that I have for you is to think about the following problem. Don't worry, I'm not going to ask you to think about how to build a bridge like the Golden Gate Bridge, but instead, here is a problem that I would like you to think about. If you were to make a workbench made out of wood, how would you go after building it? Let's say all the materials you have is a plywood panel and a bunch of lumbers and nails or screws. How do you make the structure of the workbench step by step? Of course, for those of you who have experience with woodworking, this is just a piece of cake. The reason I'm asking this question is that these sort of problems basically give you a taste of what engineering looks like. Engineers are problem solvers. Also, as a mechanical engineer, your mind should be trained to think about mechanical and structural things. So this is all to say that you have to put your brain at these sort of things, and you will see that you will get better at these kind of problems over time. How to build something, how to go after designing something, and so on. So I leave a link to a short example video on how to make a workbench in the description. You can find all sorts of these videos on YouTube. But I really want you to think about the problem before watching the video. And with that, we conclude this lecture.